Welcome to the NPTEL online certification course on CMOS digital VLSI design, and we will continue on combinational logic design part 2, which is where we have left in our previous case this part. We have seen in our previous discussion that for any logic realization you require two important points, and that important point is that you require we have seen that you require a Boolean expression, right? So you require a Boolean expression. Using this Boolean expression you can realize the logic, right? Now when you use CMOS inverter to do that, the logic will always be an inverted logic, right? So in order to achieve the actual logic, you require to put a static inverter in series to the output in order to achieve it, right? Now most of the time it is very important to see, or must be seen, that if this logic inverter which we had discussed yesterday does not allow the output signal to swing to a value larger than the switching threshold of this inverter, then this inverter won't be able to see it as a 1 or 0, right? I will give you an example. For example, yesterday's 2 input NAND gate or whatever you want to do. So if I have got a 2 input NAND gate, right, like this, and this was my design, right, A, B, and I had got A here and I had got a B here, right? So this was A, B, and this was my output, right? So this will be a 2 input NAND gate. Now if you want to convert into a AND, you have to pass it through a static inverter, and here you get A dot B, right? This is what we have discussed yesterday. But mind you, if the voltage at this particular point, so this is connected to VDD, right, and this is grounded, right? So this is grounded. If you connect, if the voltage at this point, let us suppose we name it as X, the voltage at X, if is greater than equal to the switching threshold of this inverter, then only, greater than or less than, then only you will be able to detect A dot B, right? For example, I should get a 1 here and then I should get a 0 here. A 1 primarily means that the voltage here should be larger than the switching threshold of the inverter. It might happen in some cases, in this case it won't happen, but in some cases it also might happen that this 1 will be read as a 0 by this inverter, because the voltage available at point X might not exceed the switching threshold of the CMOS inverter. So you should be very careful while designing two things. When you want to design a simple inverter by applying a static inverter in cascading with the CMOS logic inverter, you have to be very careful that the static inverter's threshold voltage, switching thresholds, are lying somewhere around VDD by 2 for most practical cases. Do not try to switch it too much towards VDD or too much towards ground. Then the reason being that this CMOS inverter characteristics which you see here, NAND gate, NAND 2 gate, will have almost a rail to rail swing. So I will actually get a VDD to a 0 swing available to me, right? So this we have learned in the previous turn, and we have also one important point before I move forward is that if an NMOS is a very good strong passage of 0, right? So if you have an NMOS inverter and the CL is charged to some value, right, CL is charged to some value, then this CL will be discharging here and the voltage here will be starting to fall down at the particular point. Now NMOS inverters are good conductors of 0, right, and PMOS are good conductors of 1, which means that whenever through an NMOS a 1 is passed between input and output of NMOS. So if I pass VDD here and I apply a VDD here, then the voltage at this point is VDD minus VTN, right? And that is the reason why you always have NMOS transistors as a part of a pull down network. So when it is a part of pull down network, it easily is able to pull the output voltage to 0, and my PMOS is generally part of my pull up network, which is easily able to pull the voltage at 1, right? So that is the reason PMOS is always a part of pull up network, right, and NMOS is a part of pull down network. right, and that is the reason why we do like this, right. So coming back to the topic which we were discussing in the previous turn, let me come to therefore the static properties of the complementary CMOS gate, right. Static properties means what? I will take a 2 input, so this example is taking 2 input NAND gate, right. So 2 input NAND gate, I just now draw here and I will just draw it for you once again, that I have got a VDD supply here, right, and then I have got this and I have got this, then I have got two NMOSes in series to each other, this is A, this is B, and I have got two PMOSes in parallel to each other, this is A, this is B, and output is taken somewhere from here, right. So what I wanted to show to you is that when you have a CMOS inverter, right, CMOS inverter, complementary CMOS inverter, its VTC, which is shown here, is data dependent, right. The type of data available to you in the input side of the CMOS logic inverter will actually determine to you the TPHL as well as the values of your noise margins, and therefore the VTC is dependent on the values of your input voltages. Now I will explain to you one by one what do I mean to say by that. So the first idea here is that let us suppose A and B were both equals to 0 and both now go actually to 1. So A goes from 0 to 1, right, and B also goes from 0 to 1. So both were initially 0 and both 1. Now when both were initially 0, please understand the pull up network was on. So this was both on because A was also on, right, and B was also on. When both are on, this charge CL was getting charged to this path as well as from this path. So the charging was very quick, and therefore your TP in the output side low to high will be very low. I hope you agree with this point, because you had two paths of charging, the effective resistance was therefore equals to R by 2, and therefore since the resistance has fallen down, the current will increase. As a result, you will be able to discharge this CL at a much faster pace, right, and therefore the time taken for the output to go from low to high will be very small. What is the other scenario? The other scenario is that let us suppose A was equals to 0 but B was equals to 1. When A was equals to 0, since this let us say this is M1, M2, this is M1, M2, I have M3 and M4, so M4. So when A was equals to 0, M3 was in on state, right, but when my M4 was off, there was no charging current, there was charging current only from this path, right, and therefore your TPLH, in this case TPLH will be slightly higher as compared to the previous case. So if you take 0 0, A equals to 0 equals to 0 and then going to 1, and another example A equals to 0 but B equals to 1, and this going from 0 to 1, in the first case your TPLH will be much smaller as compared to the second case, right, and that is the reason, which means that the propagation delay which you see in front of you is primarily data dependent, which means that it depends on the data type of data which you are feeding into the system. So with this knowledge or with this idea, let me see how this works out. So let us look at the first graph, which is the blue one which is in front of you, which basically tells you that if A and B are both 0 initially and both are going from 0 to 1, right. So both A and B were initially equals to 0 and both are shifting from 0 to 1. This is the criteria, or this is the idea I am putting here. So when both were 0, my pull up network was very strong, and therefore you see your voltage, high voltage, because so when your pull up was strong, output will be strongly connected to VDD, and therefore for a larger range of V in input voltage you will have a large value of VDD. So therefore you see the VDD is extending up to almost this point, almost this much point, right. So therefore when your pull up network is strong, when your PUN is strong, right, strong, then you allow the output voltage to latch to VDD for a longer period of time, and therefore your NMH, which is the high noise margin, is also very high in this case. So therefore noise margins will be high and your TPLH LH, low to high, will also be very, very low in this case, right. So, these two things you should be very careful about at least at this stage to understand the whole issue here. So, what we have learned therefore, and therefore, I have a strong PUN network here because both A and B were switched on. Now, let us come to an issue here, or the second case, when A was equals to 1, A was equals to 1, right, A was equals to 1 and B goes from 0 to 1, right, which is the green one, the green curve which you see in front of you. Because of this is the criteria which I am using, that for A equals to 1, B equals to 0 to 1, 0 to 1, sorry, it goes from 0 to 1. Now, coming back to the again the same diagram, if I have A here, sorry, I will just make it once again. So, I have got this NAND gate available here, and I am using that A is equals to 1 and B goes from 0 to 1, right. So, it goes from 0 to 1. So, I have got A here and I have got B here and I have got A here and I have got B here, right. So, A was equals to 1 primarily meaning this was cut off. So, this was off. So, what happens is that M3, M4 will be off, but M4 will be on, and therefore, there will be a charging of CL, but this charging of CL will be much weaker as compared to the first case, because there is only one path available to you and the resistance which was initially R by 2 has now become effectively equals to R. So, therefore, what has happened is that by applying an initial value of voltage of 0 and then going from 0 to 1, we have ensured that this is that M3 is initially off, which is this one is off, M4 is, so the charging path is basically this one, right. When A equals to 1, this was on, but this was off. So, as I told you in the previous turn that your pull down network is basically off state, and pull up network is basically in on state. Now, when B goes from 0 to 1, right, this node or this B switches on. As it switches on, the voltage output falls to 0, right, and therefore, this goes to 0 to 1, and therefore, any voltage or available here will have a route from here and the output go from 1 to 0, right. So, TPHL will be now available to you, right. So, to understand one basic criteria or one basic issue which you need to correlate, that there is a very finite difference between this and this. So, green one was when A equals to 1 and B goes from 0 to 1, and the violet one, this violet one is with the fact that B equals to 1 and A goes from 0 to 1, right. A very subtle change is there, and the subtle change is something. So, why is it like that? I will explain to you within few words as you move forward. Let me explain to you in that sense that I have again a simple inverter pair here, right, and this is grounded. So, this is A, right, and this is M2, let us suppose, and I have an internal node here INT, let me name it, and I have M1 here, and this is B, and of course, this is A, and of course, this is B, right. So, I can write down VGS2 gate to source of 2 M transistor is nothing but equals to VA is this one, minus VDS1 is which voltage, this voltage, because this is grounded, because this end is grounded, drain to source of M2 will be nothing but equals to the voltage available at this point. So, this minus this voltage minus this voltage will be the effective VGS2 available to you, clear. Now, VGS1 will be always equals to VB. Why? Because source of this is always connected to ground, therefore, this will be equals to 0, therefore, VGS1 will be always equals to VB. So, you see, even with application of same voltages VA equals to 1, VB equals to 0, the effective gate to source voltage of the second transistor is lowered by the VDS2 value. As a result, you can appreciate therefore that the threshold voltage of M2 will be larger as compared to the threshold voltage of M1 by virtue of the body bias. But remember, body bias was VSB, source to bulk. So, if your source voltage is varying, your source to bulk will also vary, fine. So, when your source voltage is varying, your source to bulk will vary, and therefore, VTN1 can be written as VTN0, right, but for the case of VTN2 I can write this as VTN0 plus, right, gamma, which is the body coefficient factor, multiplied by root of 2 phi f plus VINT, right, internal load, this I close it here, minus 2 phi f root over my basic equation. So, this is basically your VSB, remember, this is your VSB, and therefore, VNT, if you find out here, which is nothing but VGS2 is equal to VA minus VDS, therefore, this quantity gets added to VTN0, and therefore, VTN2 is larger than VTN1, which implies that therefore, my final application I wanted to say is that when the factor is that you do have B equals to 1 and A goes from 0 to 1, A goes from 0 to 1, right, you introduce a larger threshold voltage MOSFET above a lower threshold voltage MOSFET here. So, VT of M2 is always larger as compared to VT of M1 under this particular criteria. When this is true, or when if this is true, what, let us see how does it influence your overall characteristics of the device or this circuit. As you can see here, the difference between this point and this point is that as you move towards the left, right, you have a weaker and weaker pull up network, right. As you move to the right, right means your right looking at the graph, as you move towards this side, you have a stronger pull up network, as you move, and therefore a weaker pull down network, and as you move to the left, you have a stronger stronger PDN, which means to say that this green one has got a much stronger PDN as compared to the this one, right, and therefore this remains to a lower value till a larger limit of V in. So, you see, though this difference is very small, but please understand this basic issue that due to threshold voltage changes, right, you actually see a small shift. Why? Because when the threshold voltage of NMOS is larger, right, it takes a larger gate voltage to switch it on, and therefore, the pull down networks get slightly weakened. As it starts to get weakened, it moves to the right, and that is the reason this is basically to the right to that of the first case. So, we have understood, or at least given an idea how a basic VTC functionality of a CMOS inverter works on. So, let me therefore recapitulate this whole discussion. The first discussion is therefore that my propagation delay is input dependent, right. This is very important, dependent, and noise margins are also input dependent. So, if your pull up networks are stronger, right, I will get a higher NMH, high noise margin. If your pull down network is stronger, I will get a larger NML, lower value, which means that higher PUN, for a stronger PUN, your NMH is higher. Why? Very simple and straightforward. It therefore tells me that a 1 will be read very easily as 1, even if there is a noise up to a larger level, right. Whereas, when your PDN is stronger, a 0 will be read as a 0, even if your noise voltage is available to you in the below side, right. So, it can reject noise much better when you have 1 and 0 swings available to you for the pull up and pull down networks. Now, this takes care of approximately the idea that it is always noise margins and propagation delay are always input dependent, right, and that is quite interesting to look into in general scenario. Let me come to therefore the propagation delay of a complementary gate, right. So, what we do, we have already studied that I can replace individual gates, right, individual transistors by their equivalent resistance values, right. That is known as a switch model, right. We have already seen that it is a switch model, means that if I replace each transistor by its corresponding R and a switch, I can do all the activities of the device using this switch model. So, let us look at a switch model for a complementary MOS device here, which is therefore you can see on the right hand side, this is the right hand side. We have taken it from Rabai and Chandrakasan and Nikolic book, which is available. This is Digital Integrated Circuits by Rabai, Chandrakasan and Nikolic. In this case, if you look, each transistor we are replacing by its equivalent resistance and capacitance, right. So, the CL which you see is basically the load capacitance by virtue of transistor at A, and CL, this CL is again due to the second one, which is the lower one. I am assuming that these load capacitances are almost equal in both the cases. With this knowledge or with this basic idea, we can simply say that to compute the RC delay, it is nothing but log 2 0.69 into R into C. That is the what has been taught to us, that the delay is effectively 0.69 into R into 6 into C. But quite an interesting idea comes into picture. Therefore, if you look at the pull down structure or a pull down architecture, right, if you look at the pull down architecture, I require both these transistors A and B to be on in order to have a TPHL, which means that for the output to fall from 1 to 0, my both transistors Rn and Rp, which is Rn and Rn here, because of A and B transistor, both should be on. Which means that two resistors in series will add up, and therefore the overall resistance will be twice the resistance of a single gate. Agreed? So, your TPHL high to low will be something like this, that 2 times 0.69 into Rn into CL, right, where CL, assuming that they are almost equal and therefore they are in series. So, 1 by CL plus 1 by CL will be there, and automatically you get CL by 2. So, you get something like this as the overall capacitance values. But when you have both A and B going to 0, then you please see that, as I discussed in the previous slide, that Rp will be Rp by 2, because you have two resistances in parallel. This CL is basically the load capacitance at the output node, and this CL is the intermediate capacitance. Now, as I was discussing with you, that if you look at this graph here, the propagation delay also depends upon the input pattern. We have already seen this point. I will go a bit fast in this case and explain to you. See, the black one is a line which gives me the black one, which is this one, is when A and B are both equals to 1 and both are going to 0, right, both are going to 0. Now, when A and B are both 1, right, when A and B are both 1, your NMOS was, both the NMOSs in the pull down was able to discharge the cell at a much faster pace, and therefore TPHL was much lower, and therefore you see this gives you a very fast rise, and you can understand why, because both these transistors are getting in the on state, and therefore CL, this CL is getting charged by virtue of this as well as this. So, charging is faster, therefore switching is also faster, and therefore you see this red line is increasing at a very fast pace, right. So, this is what we have understood or explained. Now, let me come to the case when A is equals to 1 to 0 and B was equals to 1, right. Now, when A was equals to when both A and B were equals to 1, so A and B were 1 means both were on in this case, and the output was equals to 0. Now, what is happening is that A is still 1, right, A is still 1, but now what has happened is B has gone from B has actually, so A has gone from 1 to 0. So, A has gone from 1 to 0 means this was initially equals to 1, only this has gone from A equals to 1 to 0, which means that this is switched on, which means that I have a single path available to me to, so my lower path gets broken off, my higher path, upper part gets jammed or gets charged through this Rp value, right, through this Rp value, and therefore you see A equals to 1, B equals to 1, this notation, the violet color diagram which you see in front of you here gives you value. See, and then the last one is that A was equals to 1, right, and B was going from 1 to 0. A very subtle change is there. Subtle change is that this was, so both were on, right. So, both pull down network was on in this case, this is the pull down network was on. Now, what has happened is that B is going from 1 to 0. So, this is opened, and you again have a path available to you. From here it is getting grounded. But please understand, in the previous case when A was going from 1 to 0, the intermediate capacitance here did not have a path to discharge, and therefore you did not have to discharge that path, and therefore the violet one was moving faster. Whereas in this case you have to discharge both this CL as well as this CL, and as a result what you will get is the time taken will be larger, right. So let me again reframe the whole thing, or recapitulate the whole thing, that if A and B are both equals to 1 going to 0, that is the fastest TP-LH is there. If A equals to 1 and B going if B equals to 1 and A going from 1 to 0 is the next fastest, and the last one is A equals to 1, B going from 1 to 0 is the next fastest, and the reason we have just now understood. So if you want to, therefore let me recapitulate this whole thing, that if you want to therefore increase the delay, right, increase the delay, then what you do is you try to cascade devices in series, cascade devices in series. When you put in series, the R value increases, and therefore you will get a larger RC delay, and similarly obviously the low value will be there. Now from this basic concept, can we therefore give you any logic or criteria for the sizing of these transistors, how to size these transistors, right. Now you see, when your this output, when A and B are both 1, right, out is going to 0, right, and so there will be some path available to you. But when A and, now if you want to make your TP-HL is equal to TP-LH, which means that you want to make high to low transition exactly equal to low to high transition, suppose that is the aim with which you are starting to do, then this PMOS, so so initially A was equals to 1 equals to B, now A is equals to 1, but B goes from 1 to 0. So this is the path which is available to you for charging this CL value, agreed. Now this, if you want that the charging and discharging process times are almost the same, then you have to ensure that since the capacitance is the same, you have to just ensure that the resistance is also same in the pull up path, pull up network is exactly equals to pull down network, the resistance is same, right. So therefore I should do simple thing, that I should make the W of these devices double, right. If you make the W width of M1 and M2, right, if you make the width of WM1 equals to WM2 equals to twice its initial value, the low value, then I will get TP-HL equals to TP-LH. And increasing W by twice means basically you are trying to increase the area, right, you are trying to increase the area, R is more, right, and therefore what happens is that R equals to, remember, rho L by A. So when A increases double, R falls to half, so this becomes R by 2 and this is R by 2, R by 2 plus R by 2 is equals to R, and this is also R. And as a result you will see that whenever you want to have equal values of TP-HL and TP-LH propagation delay, you require to have the W by L ratios, at least for the NAND gate, exactly double that of the PMOS, right. If this is true what you have learned just now, I will just finish by this section by doing one more thing. Let me just do one thing, that this is basically my 2 input NOR, right. By my previous discussion I have 2 input NOR, this goes to ground, let us suppose these are all B, this is A, right, A, and this is A and this is B, right. So when both 0 0, output will be equals to 1, 0 1 will be 0, 1 0 will be equals to 0, and 1 1 will also be equals to 0. This is therefore a NOR 2 logic, right. So what we will do in the next section of the talk will be, we will be looking at NOR 2 logic and find out the TP-HL and TP-LH and how we can size the transistor here as compared to the previous cases. So we are just doing the transistor sizing, right. Thank you very much, we will meet next module.